So today we're looking at the integral test, and it's another pretty easy test for convergence or divergence of our infinite series. So let's take a look at it. If f is continuous, positive and decreasing, and f is just some function, and it's continuous, positive, and decreasing for x is greater than or equal to 1. And if our sequence, our infinite sequence that we're looking at, equals this f of x function, then the series and the improper integral will either both converge or both diverge. Okay, so it's as the improper integral goes, so goes the series, is basically what's happening. So that's a pretty simple thing. The most difficult part of it is just remembering to check for if it's continuous, positive, and decreasing. Okay, a couple important notes to consider is that when we take the improper integral, if it equals a number, that tells us that the series converges, but it does not tell us what the series converges to. So the value of the integral is not necessarily the value to which that series is going to converge. So be careful. You don't want to just grab that number that the integral equals and say that that's what the series converges to, because that's not necessarily true. And also, it's just a minor detail, but that f of x does not actually need to decrease over the whole domain. It just needs to decrease for some x greater than k, where k is greater than or equal to 1. So you could have a function that could have a little bump in the middle of it where it increases and then it starts to decrease, and that value where it starts to decrease would be our x equals k. So as long as k is greater than or equal to 1 for when this function starts to then decrease from there on out towards infinity, that's okay. It doesn't have to be right at 1. All right, so that's the integral test in a nutshell. Pretty easy. So let's look at an example. So our first example, does the series of 1 over n times square root of n from 1 to infinity converge? So you don't always want to go straight to the integral test. You want to, ask yourself, is it something else? Is it a telescoping series? No, it's not. Is it a geometric series? No, it's not. So then we'll go ahead and see if we can do this with the integral test. So first let's define what f of x is. Okay, notice the change in variable when I write this out. So this is going to be 1 over x squared root of x. And just to make my life a little bit easier, I'm going to write this as 1 over x to the 3/2, because I can think about that a little bit easier. And in fact, when we get to doing the integral, we may want to think of it as x to the negative 3/2. So the first thing we do, since we've decided to maybe try the integral test, is we need to see if it meets the criteria. So is this particular function continuous? Well, there is a point of discontinuity. It's at 0. There's an asymptote there. However, what we are concerned about is the values for x greater than or equal to 1. So it is continuous in that interval. So it meets that criteria. Is this function positive? And yes, it is. It's positive. If x is positive, then this value, the y values, will in fact be positive. And is it decreasing? And yes, of course, it is decreasing because our variable is in the denominator, and as that x goes to infinity, then the whole variable will, the whole fraction will get smaller and smaller and smaller, and in fact it will approach 0. So it meets our 3 criteria, so the integral test will apply. So let's go ahead and do the integral test. So we'll write the integral from 1 to infinity of, and I'm going to go ahead and write it as its power, x to the negative 3/2 dx. Now this is an improper integral, so we turn around and we take the limit, and I'm going to use b. Remember, you can use whatever letter you want for that, from 1 to b of x to the negative 3/2. Okay, so then this integral is simply going to be x to the negative 1/2, and so then that's negative 2 over 1. And I left out my limit, as I always do, so hold on, let me put that in there. Try not to forget that. That's very important, that limit. Limit as b goes to infinity. Now we'll write it down, x to the negative 1/2 and negative 2 from 1 to b. And so that's just going to be the limit as b goes to infinity of negative 2 over the square root of b minus negative 2 over the square root of 1. And that is going to equal, the first term is going to go to 0, so it would be 0 minus negative 2, which is 2. And as I said before, be careful, this 2 does not mean that the series converges to 2, it just is telling us that it converges. All right, so let's write out our conclusion. And we're just going to say that, and this might be something like in previous notes we've said you may want to assign this, a letter S or just anything. So we're going to say, therefore, S converges by the integral test. And there you have it. That's all there is to it. All right, let's look at example number 2. All right, so does the series from 1 to infinity of n over n squared plus 1 converge? So I'm going to let f of x be x over x squared plus 1. And then we have to ask ourselves, is this continuous? And it is. X squared plus 1 will always, it will never equal 0. It'll always have a value other than 0. So it is continuous. Is it positive? Yes. For x is greater than 1, the top will be positive and the bottom will be positive. So it is going to be a positive value. And is it decreasing? It is decreasing because the denominator is going to grow much faster than the numerator, and it's going to go to 0. So it does meet the 3 criteria. So we can use the integral test on this particular function. So we're going to take the integral from 1 to infinity of x over x squared plus 1. And then we're going to write that as the limit. And again, I'm going to use b, you use whatever you want. B approaches infinity, 1 to b of x over x squared plus 1 equals. All right, so let's evaluate this particular integral. And this is an integral you could do by use substitution, or you can see that it's just going to be a correction. Just as a reminder, let that du be x squared plus 1, so du is dx dx, I'm sorry, 2x dx. All right, so we need a 2 up here on top, and then we correct for it with the 1/2 on the bottom, and so we can go ahead and take this integral. So this is simply going to be the integral, the ln, let's do the limit as b approaches infinity of the ln of x squared plus 1, and we've got that 1/2 we need to put in there, and instead of having it inside the integral, I'm just going to stick it out front because I can multiply it by the limit at the end, and that's fine, it doesn't matter. That is a legal maneuver, and it's going to be evaluated from 1 to b. Okay, so a little messy, sorry about that. I think you're used to it by now, unfortunately for you. So that equals 1/2 the limit as b goes to infinity of the ln of b squared plus 1 there's my cat if you can hear it, minus the ln of 1 squared plus 1. And this just equals the limit, 1/2 the limit as b approaches infinity of the ln of b squared plus 1 minus the ln of 2. And when we plug infinity in, there's nothing we can do about it, and it's going to stay there forever and ever. So this goes to infinity. So we would say, therefore, and I'm going to let S equal, therefore, S diverges by the integral test. That's all there is to it. So give some of those problems that are listed on Blackboard a try. Let me know in class if you have any questions, or you can send me an email if you're doing this in the evening. Have a good day.